Well, can you hear me? Yes. Yes? Okay, I'll do that. Thank you very much. Of course, I'm very, very, very happy to be here. I think that your community is incredible, and I already had contacts in the past with the BAA and the AVSO, and both are very impressive associations, so I'm very happy to be here with you. And thank you for the invitation. I will talk about, the idea is to talk about how to start in spectroscopy. So really the beginning. You have seen yesterday in many presentations, people are talking about the spectra, and what I'd like to invite you now is really to do yourself spectroscopy. So I do a short introduction. I see why we are doing spectroscopy. We'll see how it works in the field with your telescope, how it works inside the telescope very quickly, and we'll talk about data reduction, and at the end I will give you some recommendation. Okay? So, well, I'm the boss of Sheliak Instruments, so I know that within an association I am on the dark side of the force. I am on the business side, but I promise that if we created this company more than 10 years ago now, it's really to serve the community, the astronomical community, and my first priority is to develop spectroscopy. Of course, I'm the manager of the company. Of course, we have to make money and profit to be sure that we'll still be there in 10 years from now, but my deep motivation is to develop the spectroscopy all over the world. As David said, I've been involved in the design of several instruments like the LARIS 3, the LP, the LISA. So of course I didn't do it alone, especially I did it with the incredible help of Christian Buil that everybody knows here. So in few words, he already designed, he was the creator of the instruments, and within Sheliak we made it exist, and we made it happen for real. Okay, and I'm also involved in the community. I was at the beginning of the BESS database and the ARASBeam website, which is a program to observe the BE stars. I'm also involved in the OHP SpectroStar party, so I'm organizing every year this star party. It will be next week. So OHP is the Observatoire de Haute-Provence, so in Provence, in France. And you are welcome to participate. We do it every year in summer, and well, again, it will be next week, but it is full. So but you can plan it for next year. And I've also written a practical guide to start in spectroscopy. At the beginning, it was in French, and it worked well. And now we have, thanks to few people in the room, we have the English translation. So if you're interested by what I will tell you in few minutes, then you can continue and have much more information. Okay, and my deep motivation is that I've understood that if you are doing spectroscopy alone in your backyard, this is very interesting, this is fun, but you will not get a lot of results. But if we all work together and we observe in a coordinated way, then we really become, for the community, we become a new kind of instruments. And 10 years ago, for the professionals, or 15 years ago, we were not serious. But today, there are a lot of collaborations between amateurs and professionals. And really, this is what is interesting to me. Okay, so this is why I came here. This is to motivate a lot of people to jump into spectroscopy. Who in this room, can I ask you the question, who in this room is doing photometry? Can you hold? Okay, so about half of the people. Who is doing spectroscopy today? Oh, almost the same. I'm surprised. This is not the result I did expect. Okay, so no, what is very interesting is that you already have a lot of people in this room doing spectroscopy, and this is really this is one of the reasons I've written here. This community is growing, and for sure, if you start in spectroscopy alone, it will be a little bit difficult. But if you have a community, it becomes very easy, because you will have people to help you to do, because for sure you have many questions at the beginning. And also on top of that, remember what I told you, it's important that we work all together, and thanks to this association, so especially here I'm talking about the BAA and the AVSO, you have all the data you can catch are really valuable, because they will be used, because they will be put in a database where any other astronomer can use it to produce science. Okay, so this growing community is something which is very important. But anyway, I come back at the beginning of the slide, the first reason for me to do spectroscopy is that when you do photometry and when you look at variable stars, so you see that the photometry is changing over the time, but you don't know why. When you do spectroscopy, you are starting replying this question: why is it changing? What is changing inside the star? Okay, this is really the first reason. We start just observe phenomena, but we start understanding these phenomena. Okay. By doing spectroscopy, you can do, when you are doing science in astronomy, you can do photometry, so you used to do that. You can do astrometry, so measuring the position of the stars or the objects, so mainly in the solar system. And you can do also spectroscopy. When we are talking about science, it's almost all, okay? But what I can tell you is that in spectroscopy, this is really a never-ending story, because you can do physics, you can do chemistry, you can do mechanics with all the movements and so on. So there is a lot of things to do with spectroscopy. This is a very universal tool, okay? Another important point to do spectroscopy is it can be done in city center, even if the weather is not perfect, okay? Well, I have been told that in UK the weather is not always perfect. This is not my personal experience today, okay? But in case of, just be aware that you don't need to have a perfect sky to start in spectroscopy. Of course, it is always better to have a good sky, of course. But you can really do science in a city center. By the way, you probably know Valérie Desnoux, who is the girlfriend of Christian Bril. She is in Paris. She has an apartment in Paris, and her telescope on the top of a building, and she is very close to the Eiffel Tower, and she is producing wonderful science. Okay, so that's real. And of course, perhaps the most important reason is that spectroscopy is fun, really fun. It's really fantastic, because you can see that the object change permanently. Not all of them, but a lot of them change permanently. You can see the rotation and the pulsation of stars. You can measure the sun mass in your backyard. It's just incredible, you know. And you can measure galaxies' redshift. You can discover new events, and you can do a lot of many other things. Okay. By the way, about discovering new events, I don't know if you are aware. A few days ago, there were an announcement for nova, and Olivier Garde, who is a friend of mine, who now works for Cheliac for some months, he was the first in the world to produce a high-resolution spectrum of this star. So it's fun, and it's fantastic to have this kind of announcements. Okay. Now, how it works for real? We're doing. You have seen spectra yesterday, and how it happened for reals. Here is my setup. So this is a C8 telescope, so quite basic, and this is an LP spectroscope, okay, from Cheliac, of course. And this is the instrument I recommend to start with if you don't know exactly what you want to do. Okay, so this is what we call a low-resolution spectroscope. The spectroscope itself is this small part. Okay, so it means it is really that long. It is very, very small. Okay, and you have a guiding system here with this camera, and you have a calibration box to make sure that you have calibration lamp to take good spectra. And this is, of course, the acquisition camera. Okay, so you put this instrument between the telescope and the camera that you used to use. Okay, And on top of that, we add the second camera to see where the telescope is looking at, okay, to see the field of view of the telescope. And in addition, personally, I like to have a third camera, so some people can be impressed, but for me, this is really to make my life simpler. To have, well, this is in fact an electronic finder, which allows me to know exactly where I am in the sky, and I can be sure that I catch the right star. Okay? Now, of course, because you have put you have removed the camera from the telescope and you have put the spectroscope between the telescope and the camera, you don't see anymore what you usually see, so a wide field with a lot of stars. You see something like that. Okay, so this is a line. So this is a spectrum of one star. Okay, and with this software, which is Demetra, I talked about it again later, you can in real time display the profile of this line, okay, and this is what we call the spectrum, okay. So imagine that this is the blue part of the spectrum, this is the red part of the spectrum, this is H alpha in this region, or this one, no, this one I think. So if it were in color, you would see a wonderful rainbow all around this line, okay. And in fact, the job of the spectroscope is to spread out the light and to transform the color or the wavelengths in a position on the sensor, on the CCD chip, okay? How can it work? In fact, in the middle, at the focal plane of the telescope, we put a slit, a very thin slit, which is 20-25 microns wide, okay? And this is all the light coming through this slit, which will be spread out in the spectrum, okay? So in this case, you can see here that there is a star in the middle of the slit, and there is a spectrum in the middle of the image. And here, there is no star, of course, but you have the sky background, okay? And in this case, I have chosen the threshold of the image to make visible this background. In fact, by doing that, we measure at the same time the pollution spectrum, okay? And this is very useful because you can correct your spectrum from the background, from the pollution background. Okay, this is one of the reasons for which we can say that you can do spectroscopy in city center, even if there is light pollution. Okay, and in this system, which is the guiding system, in fact, all the other stars in the field are sent back to the guiding camera because this plate here is a mirror. Okay, so imagine that there is a mirror here with a hole, with a slit inside, which is engraved, and then there is a hole. So if the light is outside of the slit, it is sent to the guiding image. If the star is in the slit, its light is sent to the spectroscope. Okay? Now, how it works inside the instrument. Imagine that you have the slit here. So it is perpendicular to the plane of the screen, okay? So it makes a kind of point-like source. And then this point-like source will send light in any direction. And here we have at the entrance of the spectro a collimator lens that will transform this beam in a parallel beam, in a collimated beam. Okay, and this will be sent, this parallel beam will be sent to a dispersion element. So it is either a grating, dispersion grating, or a prism. Okay, and these are really the two solutions that we use. This effect, this element will have as an effect that all the rays with the same wavelength or same color going out will have the same direction, okay, look at the red lines here, but for another color, another wavelength, they will be all parallel, but the angle will be different from the other wavelengths. Okay, so in this case, we have the blue rays that goes in this direction, and all the red rays that go in that direction. And after that, we just have to put another lens, an objective lens, that will reform refocus the element on the sensor, on the CCD chip. Okay, and then all the blue rays will arrive at this point, and all the red rays will arrive at this point. Okay, this is what makes physically the spectrum. This is purely optics. This is very basic, in fact, and this is very, at the first level, this is very basic optics. Okay, here is an illustration for the LP. So I remember the LP is that big. Okay, but anyway, if I look at it. So we have a slit inside the LP. We have a collimator lens here. So we have at the exit the parallel beam. We have what we call a grism. A grism is a combination of prism and dispersion grating. Okay, and that makes the dispersion of the rays. And then we have the collimator behind. Okay, and by the way, if you remove this part, or you can see that you can remove this part here. Then you can remove this lens from the system, and then you can look at it by eye, and then you will see a spectrum with your eye, okay? And of course, at the end, the objective focused the image to the detector, okay? Are you silencious? It's normal, yes? Yeah. Okay, see, these are, once you have understood that, so the spectroscope, the job of the spectroscope is to spread out the light that comes into the slit. Okay, here are a few examples of spectra that you can have. This is a sun spectrum on the top, a high resolution spectrum. You see that we are in the green part of the spectrum. And the spectrum is wide because the sun, I think it was a spectrum of the sky, in fact. And then this is an extended object. And then all the slit is illuminated with the same light. So as a result, you have a wide spectrum. Okay. Then below you have a comet spectrum with the core of the comet, and you have the tail with some gas that makes this extension there. Okay, this is a standard star spectrum, very common spectrum in high resolution. Also, we can see a lot of absorption lines, like in the sun here. This is calibration lamp. Okay, in this case, this is a neon lamp spectrum. Okay, we illuminate all the slits with neon light, and as a result, you will have only few emission lines that correspond to very precise wavelengths. Okay, and we use this type of spectrum, this type of calibration spectrum, to make the calibration of the spectrum at the end. So we can say that this pixel position is at this wavelength because we know the pattern of the neon. Okay, so these are, well, I would say hot star and cool star. I'll talk about later. And this is also something very interesting. This is Jupiter spectrum. If you look at this image, you have some banded or slanted lines, absorption lines vertically, and some of them are vertical. Okay. That's strange. In fact, this means that Jupiter is rotating, okay? Because the vertical lines are the lines from these are the telluric lines, so the lines from the Earth's atmosphere. They are not moving. But the banded line, the slanted lines, are the ones from the planets. And the planet is rotating, and this rotation by Doppler effect will change and will give an inclination of the spectrum. So by this image, we can measure the rotation of Jupiter. On the left, you have only what we call 2D images. Okay, these images are really what you will see on your sensor or your image when you take the spectrum. But at the end, what is interesting is to have this kind of spectrum. Okay, and going from one to the other is what we call the data reduction. Okay, and it's important to understand that there is a lot of operations to go from here to here. And something very important also is that, like in photography, you can have a wide-angle lens or you can have a tele-lens, and both of them are interesting, and you cannot do the same with both of them. In spectroscopy, this is exactly the same system. You have low-resolution spectra with a wide domain. So this is the whole visible domain from 400 to 700 nanometers, and you can also work in high resolution to see a lot of details in the spectrum, okay? And this is here a zoom in the H-alpha line of this profile, okay? And you see here that there is a lot of lines that you cannot see here because you don't have enough details. And these are, most of them are telluric lines. Okay, so the resolution depends on the optical schematic of your instruments, depending on the lens, focal length, the number of lanes per line, sorry, number of line per millimeter, sorry, in the grating, and so on. So it depends on the geometry of your instrument, and you can then decide either to do low resolution or high resolution spectroscopy, and both are very interesting. By the way, here you have a wide range, and you also have short exposure time. Okay, in high resolution you will see a lot of details, okay, which is better, but you only have a very small wavelength domain, and you will have much more exposure time to get this image than this one, because each pixel receives a very few parts of the light that is coming from the star. Okay, so here are some examples of what we have made recently. It was in May this year with the ALPI, with the exact configuration that I've shown you. So this is Arcturus. Well, this is typical for a cold star, a cool star, and well, you can imagine that there is some noise in your spectrum. In fact, this is not noise, and I can prove it because the next slide is done exactly in the same condition, but this time this is a hot star. Okay, and in a hot star you see that the profile is very smooth, and you have deep, very deep lines from the hydrogen. Okay, so these are very typical. You can have also very different objects, like YCVN is a carbon star. I guess that you already have seen with your naked eye a carbon star in the telescope. It is red, red, red. We can see it. It's only in the red part. All the energy is on the red part of the spectrum. Okay. This is a BE star. You have seen that on this image, the H-alpha line, so which is H-alpha means the first Balmer line, the first line of the hydrogen, which is the first element in the universe. So generally speaking, this is the most important line. So usually it is in absorption. Okay. In the case of a BE star, it's in emission, and it can, depending on the star, it can move over the time, so it can change. So this is why BE stars are so fun and so interesting to follow. And this is a planetary nebula. Yes, it's a planetary nebula. You can see only some emission lines, and there is almost no what we call the continuum, the continuous line. Okay, I'm going fast because I see I'm late. Regarding the data reduction, so we have to switch to go from this image to this profile. This is the same star. This is YCVN. Okay. How it works? First, we have to consider that an observation, a spectroscopic observation, is a consistent set of images. Okay. When you do an observation, you must get the target star spectrum, of course, like we have shown with the YCVN. You have to take bias, darks, and flats. Like in imaging or photometry, well, the flats are a little bit different, but the idea is exactly the same. And on top of that, you must have calibration spectrum to be able to calibrate your spectrum, know on which pixel is which wavelength. And you have to also to take a reference star spectrum to be able to calculate the response curve of your instrument, because the instrument itself has a very important response curve depending on the wavelength. Okay, so if you are using Demetra software, so Demetra, this is a software that we developed recently. We have made it available recently within Sheliak, and the idea is really to make our life simple. Okay, because a lot of people who started in spectroscopy said, wow, the tools are not easy, so we wanted to do something really simple but with a very high quality result, okay? So the idea here is that we have a list of observations, and for each observation we have the different baskets that we need to collect with the object, the bias, the dark, and so on. And the idea is that if it is green, so it means that you can go to bed because you have collected all the images you need to process your data, okay? And if one of them is empty, then it will be in red. And if you need to acquire an image, you can just click on this button and it will open another window that takes care of the acquisition. So Demetra, the idea of Demetra is really to go from the acquisition to the data reduction. Okay, and then in this case, because this is for spectroscopy, you will have some useful tools. For instance, we'll detect automatically in this image if there is a saturation. Okay, this is very important to make sure that your data is of high quality. And the data reduction itself is made of several steps, and this is why it can be quite complex, in fact, because you have different steps to go through. But again, in the Demetra software, we have a data reduction tab here, and we have all the steps here, and they are even more detailed. And the idea is that you can do the data reduction in one click here. It will do all the reduction in a few seconds. But you can also, in fact, I absolutely don't want to give you a black box and say, well, push on the button and the data will be correct. So this can never happen, and it's very important to say that you are responsible of the quality of your data. So we have made a system, you can go step by step and run each step one by one and check what happens before and after the processing, okay? So, but the idea is that we want to have something very automatic, fast, but serious and of high quality.
4 minutes, please.
Yes, I've almost finished. Now, a few recommendations when you start in spectroscopy. First is really make your first spectra on a bench. Please don't, when you receive your spectroscope, don't put it right on the telescope. There is almost no chance that you can have a correct spectrum, okay? The telescope is an instrument, the spectroscope is another one. You have to tune them separately, and when you master them, when you control them properly, then you can attach them together. Really, this is probably the most important advice that I can give you, okay? By the way, train yourself with your telescope. Well, because most of you are experienced observer, I guess that you know what it means, but you must be able to put any star, any faint star, at any position in your image. So you have to control that, okay? An observation, again, is a consistent set of images. This is a key to make things simple. Usually we collect all the images, and the day after we thought, well, okay, in which order did I do that, which image is with what, and so on. No, an observation is a consistent set of images, and really think that the core of the process is the data reduction. It is not the acquisition. Okay, for most of observers, the acquisition is great. It's the great moment and the most important. And we say, oh, okay, I'll see tomorrow or the day after how to process my data. In fact, this is the wrong way to think. The central process is the data reduction, and then the telescope is only there to produce the right image to fit in the process. And by doing this way, you will reduce your data in one click, really. Okay, and. I'm very convinced by the continuous improvement. Well, a small step every day. I'm doing that, so always go to basic, simple. Spectroscopy, really, it is simple. But there is a lot of parameters to put under control. The only complexity is there, okay? But there is no step which is really complex. So take your time to go step by step and don't try to go too fast, okay? Observe regularly. And this is feasible because this is spectroscopy, so you don't have to wait for the next vacation to be sure that you'll find the right place. You can do some steps, small step, every day at home. And well, never let your computer make the decision for you. Again, this is something very important. I know that in the middle of the night, we don't think the same way. as during daylight, but it's important to always understand what we are doing, okay? And of course, this is very, very important. Share your results. This is by far the best way to progress and to have great results, because at the beginning you don't know how to compare yourself to the others, and I know it's always frightening, but in fact this is the key. When you have your first data, share it and ask people for feedback and compare to the others, and this is the best way to have a good result, and I promise that quickly you'll have perfect data and we have all the same level when we collect the data. Okay, and again, well, there is a book if you want to continue this thinking, and I thank you very much for your attention.
Excellent. Thank you, François.